Good morning. Today is June 10th, and this is the John Chappell Natural Philosophy Society, a Saturday science chat where we talk about everything mainstream won't dare to touch. And I believe we have a conversation already started with Bill Lucas and Bob Gray, and perhaps we'll investigate magnetism today. And I have our one slide here. We do have our conference coming up July 19th to 22nd. So I hope that people will come and participate in that conference. And I'll be there. And I was telling Bill that I'm working on a paper I will be presenting, which is how to win the Nobel Prize by finding the ether particle. Since the only thing that seems to be required to win a Nobel Prize these days is to find a new unique particle. And what better particle to find than the particle that makes up space? So you don't want to miss that. That will be groundbreaking. Or yeah, that'll be funny. But in any case, please come. So let's go ahead and get the conversation here between Bob and Bill. So you're asking about the nature of the magnetic fields.
Okay. Before I get into that, I'd like to give you the reference to the conference call software that's free that can do up to 1,000 users. It's called freeconferencecall.com.
Freeconferencecall.com. Well, that's a pretty obvious name.
Right. And so anyway, I signed up for that, but I haven't used it yet. But that's the name of it. And if CNPS needs, has to pay for the extension of the Fuse conference call, they might want to look at that because it can handle more simultaneous users and it's free. But I'd try it out first, and see how it works. But
yeah, maybe they spam you with ads or whatnot. Who knows?
I don't know. So I haven't tried it. So anyway, that could be. Okay. So getting back to was it Bob's question? We were talking about monopole. Magnetic monopoles, and the normal solution to Maxwell's equations pays great deal of attention to the one of the equations, which is del dot B for the magnetic field equals 0. If you have magnetic monopoles, del dot B is equal to something. And so if magnetic monopoles exist, then the solution to Maxwell's equations, which include del dot B equals 0, is to say that B equals del cross A, where A is the vector potential. And so that means, but mathematically, del dot del cross A is, for a vector, is always equal to 0. So
although Bill, most of that kind of stuff doesn't really mean anything to most people. I mean, is there a way you can explain that in a more intuitive fashion? Because people don't know what del.
Okay, del is
that sort of thing means.
It's a three-dimensional.
So I'd like for him to continue.
So it's a vector identity that del dot del cross A is equal to 0. For A is any vector. And so when Oliver Heaviside was converting Maxwell's equations from the what do you call them? Quaternions, yes, thank you. From quaternions to vectors, because he thought vectors were easier for scientists to understand and to work with. He named this particular vector that was the solution for the magnetic field the vector potential. It has nothing to do with potential energy or energy. It's just the name he gave it. And the reason that Heaviside liked that was because when you do that, Maxwell's equations can be reduced to a differential equation for the vector potential and a differential equation for the scalar potential, psi or phi. And and those two equations are basically identical, so that there's what's called a covariance. That means that the scalar potential and the vector potential obey the same equation. And that was considered beautiful, that symmetry. And ever since that time, that symmetry has been considered a standard to be met by any theory. So when later, when Einstein came out with his special theory of relativity, and they were able to, using the vector potential, to combine that into Maxwell's vector equations, they still had that same covariant symmetry. And so it was considered a further proof of the validity of special relativity that it maintained that symmetry. And so the idea of symmetry has become a very important notion in modern science. And that's where it originated with Maxwell's equations when they were converted to vector form. So then the question is, well, how can you find a magnetic monopole to confirm or deny the del dot B equals 0 equation, the empirical equation? And the form that B has to have, the magnetic field, in order to satisfy that equation, is it must be a closed loop, and it must have a north and a south pole. And of course, if you look at a bar magnet or a typical disc magnet, you'll see that each end or side of the magnet one has a north and one has a south pole. And if you look at a compass or put iron filings on a piece of paper above the magnet, you can see the field lines, the magnetic field lines, and you can see they go from north to south. And you can see that they form a closed loop. So that is the basis of this idea. But in modern times, if you go on the internet, you'll find a lot of magnet companies selling monopole magnets. And some of them call them unipole magnets, but a unipole magnet actually has a north and a south pole. It's just that if you were to put iron filings around a toroidal magnet that was a unipole magnet, the iron filings on the outside of the toroid would be going away from the center of the toroid. And but if you look inside the toroid, you can see the south pole or the opposite pole that's there. But on the outside, they appear to be going radially outward. But it's really, that type of magnet is composed of, if you were to cut it into little segments all the way around the toroid, you'd see they're all dipole magnets that are in that segment, in those segments. And that's the way they make it. They take a bunch of dipole magnets and they put them together, and then there's a ceramic magnets, and they can melt them slightly and cause them to cohere together. And but if you drop it on the ground, when I did one, it just busts apart because it's just barely held together. And but it's not a real, the unipole magnets are not a monopole magnet. But you have a monopole magnet at your house and you may not even realize it. Some of you may have refrigerator magnets. And I have some at my house, and they have like a picture on them. and the backside is a dark plastic. And if you get a compass out, or you get two of these, just say you take two of these um, refrigerator magnets. They usually are used to advertise something or have a picture of something on it. They send it to you in mail and you put it on your refrigerator to remind yourself of that. If you look at that, um, you'll see that the two dark sides, the dark side of one and the dark side of another, will go together like a regular magnet. But if you flip them over, so you would have the opposite pole, they don't go together and they don't repel. They just ignore each other. And then if you rotate the magnet, the two magnets when they're going together, the dark sides of the two refrigerator magnets, you will find that if one of the pictures is perpendicular to the other, they don't go together. But if you make them so that they're on top of each other, so that the pictures are aligned, if you flip it over, it's the same picture in the same orientation, then they will stick together. And also, if you pull them slightly apart, you'll discover they are very tightly bound and they kind of click from one position to another. And that clicking indicates there's some kind of structure there. But anyway, if you use a compass, it looks like that's a monopole magnet. But that's not what is sold as a monopole magnet. The monopole magnets that are sold have only one pole, and you can't find a second pole with, and they make them out of these neodymium materials, so they're very strong magnets, and you would have no trouble finding the South Pole if there was one because they're so strong. Uh, so anyway, that's the current situation, and what I'm trying to do is to buy a bulk amount of these monopole magnets and take it to scientific meetings and let people purchase one for $1 or whatever. So and I'll have provide compasses so they can test them right there at the meeting, and so they can take one home and do their own experiments on it to see what is the case. And so I think that's the fair way to let everybody do their own experiments. And so that's what I'm working on, and I hope to be able to do that for the CNPS meeting next year if it's held on the East Coast. And so if you come to that, I hope to be able to provide some of these magnets. You can just buy one at cost, and I'll be buying them at the rate of 1,000 at a time. So you get a good or low price. One of the toroidal ring magnets, the unipole magnets I bought was $150. So it gives you don't want to pay $150. You'd like to pay more like $1 for one of these. And so anyway, that's the situation. And
So, Bill, I'm trying to understand if we have to modify the classical Maxwell's classical electrodynamics, put in that there is a different kind of particle, which is a monopole, or is it only a different configuration of currents, and the electric currents are configured in a way to result in an external monopole structure?
well, the answer to that question is very interesting. And I'll give you a little history, first of all, of science so you can kind of see how we got to where we are. When um, Isaac Newton was developing his theory of gravity and his theory of the force of inertia, he was able to take the empirical equations of people like Kepler, and he was able to derive from that an equation for the force of gravity. But his equations were only proportional equations, and he wanted to put an equal sign in the equation to put it into mathematical form so that it could be tested more completely. So in the case of inertia, the equation today is F equals the mass times the acceleration, where the mass is the inertial mass. He really only had F as proportional to the acceleration. The inertial force of inertia is proportional to acceleration. And so he put an equal sign in there, and he had to put a constant. So he put a constant in, and then eventually he called that constant mass. But when the other scientists asked him, what is mass? He said, I don't really know. He said, I can give a number for it, but I don't know. And so what he did, they asked him more questions, and he says, well, what is the force of inertia? And he says, well, the force of inertia is the force between what we call matter, pieces of matter, and I don't know how that force is transmitted. And then when it came to gravity, he had two masses involved, and so he had gravitational mass 1, gravitational mass 2, and he had another constant called g, because if he put in the same mass for the inertial mass as gravitational mass, he had to have different properties, so he had to put another constant, g. And no theory of gravity until recently has ever been able to define what mass is, or to define what g, big G is, from theory. They can do experiments and say, well, if F equals big G m1 m2 over r squared, and m1 is the same thing as F equals ma for the inertial mass, I can measure a value for the mass, assuming inertial mass and gravitational mass are equal, and I can then get a value for big G. But I'm doing that only by experiment. I don't have a theory that can explain what it is. And but what happened was a number of things happened over time. One is Arthur Compton was measuring, making measurements on electrons, which are very simple particles, and he discovered that the electron has a wavelength associated with it. And a wavelength was not what you normally would associate with a particle. So there was a logical contradiction. But the way it got handled with the development of quantum mechanics was they had the particle wave duality, which was a fundamental assumption of quantum mechanics, and it says a particle can have a wavelength associated with it. But Arthur Compton's last graduate student, Winston Bostick, performed a series of experiments in which he falsified that assumption of quantum mechanics, because what he was able to do was he was able to make what's called a soliton, or standing wave, a permanent standing wave, in the electromagnetic field, and it was in the shape of a toroidal ring, which had a wavelength, which was the circumference of the ring, and it was just composed of the field. Now, that thing that he made, which was called the soliton, had the properties that we are assigning to charge. But what he was able to see was it was entirely due to field. The field, the electromagnetic field has tensile strength, and different structures in the field can attract and repulse one another with nothing called charge. So the concept of charge was something that we imagined in order to put an equal sign in our equations, like Coulomb's law and stuff like that. But the fact that there's a wavelength associated with these charges or particles, elementary particles, shows that it is really something related to the field structure. And so the field structure has a wavelength, and that is what we see when we do experiments. And so you can do an experiment in water, and you can see, in any fluid, you can see the same effect. And of course, all these fluids have the electromagnetic field there, and that is what is causing these things to happen. And so anyway, the concept, if what we call charge doesn't really exist as an entity, but it's just a figment of our imagination, so that we could write down an equation like F equals Q1 Q2 over R squared for the Coulomb's force, then the most important thing is the field. And then the question is, well, where does the field come from? And it is interesting, if you go back to the earliest philosophers, the Greeks, the Indian Jains, and even Moses, they all say that the field emanates from God, and that is the source of the field. And so all the structures in the field are just things that are made by changes that occur in the field, ripples in the field, the kind of changes that Winston Bostick used in order to make these toroidal rings. And by the way, the toroidal rings don't have regular properties that we would measure. They don't have mass, they don't have charge. They do have a wavelength, but those properties from ancient philosophy have always been known to be produced by the geometrical combination of those toroidal rings. And that geometrical combination can vibrate. That kinetic energy of vibration is what we call mass, it turns out. You can define mass that way, in which case you don't have something called mass, you just have a vibration of these solitons. And charge is the tensile strength force between different structures of the field. And so charge is related to that. But it's not a physical entity like we would normally assume, and is assumed in modern science. So that's kind of the background of where we are. So the question is, if you don't want to, if you're not religious, for instance, you don't want to acknowledge that God is the source of all the fields, which is the source of all the particles, that so-called, and all matter. But the Judeo-Christian religion says that God created all that from these fields, but science doesn't want to acknowledge that today, because science is controlled primarily by the non-religious sector of society. Now, there were times in the past, like in the days of Maxwell, where that wasn't the case. And what was called the field in those days, they called the Spirit of God. And it's in their original writings. But we've deliberately forgotten that, because we don't want to acknowledge that religious component that's there. But so anyway, if you don't want to acknowledge the religious component, you will insist that there is something called charge, and there is something called mass, and there are particles, and the particles are the source of the fields. That's what you would have to insist. That's the only other alternative. And then the Big Bang creates matter from nothing. You don't need a God or anything. You just have the Big Bang, which is a statistical fluctuation according to quantum mechanics. But Henri Poincaré gave the death knell to those ideas when he invented the field of meta theory. Meta theory is the logical theory of theories based on logic. And what he does is he proves theorems. And one of the theorems that he proved, that Poincaré proved, is that a theory, a fundamental theory, can have fundamental constants in it, but no other fundamental theory can have any of those fundamental constants. So if I have the theory of electrodynamics, and I have a fundamental constant c, the velocity of light, of transverse light, then what Poincaré proved was you can't have a theory of special relativity or a theory of general relativity involving c, the velocity of light, because the fundamental theory for that is electrodynamics. And
Now,
so,
Bill, I think we're getting a little bit far afield.
okay.
I mean, so Bob, is your question being answered? Because Bill is telling us a lot of stuff, but I don't know that he's.
It's all interesting. It's all interesting stuff too.
But is he answering your question? Just want to make sure we get back on track.
What's the link to the paper that you had up there?
Well, that's the. So I was showing Bill's paper on the monopole, and Bill sent that to me in an email. But I'm sure that's your common sense newsletter, right, Bill?
Right. If you want to send it out, you can send it out to them. It's available for free from our website, commonsensescience.org.
I couldn't find it.
No, should be out there.
Well, it may be that the webmaster hasn't put it up yet.
Okay, well, that might explain why I couldn't find it.
Yeah.
Well,
I can send it out to everybody on the mailing list if you want.
I'm not sure I'm on the mailing list, but
I mean the list for this conference, this video conference, Fuse conference.
well, that would be nice, Bill.
Okay.
You could send me a copy. I'd appreciate it.
Sure.
And if you don't, do you have my email address, or should I send it to you in the chat?
I guess
I think you probably do.
Chat. My system is just slowly coming up to par.
Okay, well, that would be appreciated.
Yeah.
Okay, so I have these refrigerator magnets here. Okay, and basically, if you have a magnetic viewer, and I've done this. Okay, here's the refrigerator magnets. What Bill said is substantially correct. If you let's see, if you got my camera, I turned the camera on.
Yeah, we can see you, Harry. You got the refrigerator magnets?
If you look at both sides of the magnet, you put them together, they don't stick. Okay. If you put the opposite sides together, they do stick, but not. Okay, there we go. Okay, if you put them at right angles, they stick very poorly, but the magnetic field is in stripes in the plastic. And if you slide them together with the two back sides, they click together because they're like quantum jumps, because the magnetic field is in stripes. Okay.
Right. Now the question is, why is it that the opposite sides of those magnets won't?
Well, Bill, I'm not really an expert on this. I know that I have viewed these things with the magnetic viewer, and so I'm not really familiar with exactly how the magnetic fields of these things do, but they're laid down in stripes. So if you look at it with a magnetic field viewer, you'll see that the magnetic field is stripes.
Right. But what you should have on the other side, you should have the same stripes. And you
well, I'm not really sure I understand exactly how this works. It certainly is an interesting point.
Right.
Okay.
But what I'm trying to get is
it's certainly true. If you can see me, that doesn't stick. They don't stick together at all. I mean, if you put the printed sides together, they do stick if you put the back sides together.
That's right.
They don't stick very well if you put them at right angles to each other. They sort of, they're sticky, but not, they'll still fall.
Yeah.
Okay? But if you put them aligned properly, they stick together.
Right. Well, if you have monopole magnets, you can't have a planar magnetic field. You have to have a three-dimensional field.
Well,
my only point, my only point about this is that it might be helpful if there are these things called magnetic field viewers that really are pretty helpful in visualizing the magnetic field.
Right.
And so,
I'm using those. I'm using iron filings and I'm using compasses, and I've ordered the guaranteed magnetic monopoles that are three-dimensional, only one pole. So,
well, my view on the magnetic monopole is, and I think we talked about this before. When people use that term, they mean they're referring to an elementary particle that's analogous to an elementary particle like an electron or a proton or something like that.
right.
And this would be an elementary particle that is nothing but that has the same field alignment as the electric charge an electric particle would have, like a proton or an electron. But it seems to me if that were the case, then you couldn't say there was a difference between the magnetic field and the electric field. And so any particle that would be identified as a magnetic monopole would turn out to be just another charged particle with electric charge because you can't tell the difference. So that's, to me, that's an issue. The electric field has to be different from the magnetic field in some way. And in my mind, the difference has to do with the topology of the field, which is the electric field terminates on what's called a charged particle, and the magnetic field doesn't terminate anywhere at all. It just reconnects to itself like the snake eating its tail.
Well, you may not be aware of this, but I was an invited speaker for an international conference that was held by the Spanish government in 2005 in the Canary Islands, and I presented there using this idea that the all elementary particles are made of solitons, and there's multiple solitons in each particle. For instance, the electron has 3 solitons, the proton has more, and the neutron has more, and the pion and the kaon. And from the geometric structure of the solitons, you can calculate the mass, you can calculate what we call charge, you can calculate spin, and you can get it for all the confirmed elementary particles, which is over 96. And the standard model of elementary particles can't do that.
Well, I think that's really great, Bill. I guess my point, I don't disagree with your point in that I think mainstream sort of, they've locked into a certain set of concepts that they consider to be sacrosanct, and it's really kind of hard to shake them out of that, the mindset that they've established that only the way they do things and only the way they think things and only their assumptions are the correct assumptions. That's, obviously a problem.
Yeah, it is. And I agree with you on that. And the problem boils down to the scientific method. And what has happened is the scientific method has been changed to remove the role of logic. And when you remove the role of logic, you can no longer falsify any theory in science because it involves an assumption that has been proven false.
Bill, I have another question for you.
Okay.
Are you Charles W. Lucas Jr., who wrote The Universal Force?
Yes.
Okay, great. Where's volume 2 and 3? I'm waiting for volume 2 and 3.
They're in my computer, but they're not finished.
Yeah.
And I do
Okay.
have published papers that will make up part of those volumes, but I don't have all of the research done. It is amazing when I go back, now that we have the internet, many countries have put up online their science history going back thousands of years. And now we can see what they thought, what they believed, what their logical minds gave them. And what we find when we go back before, let's say, 300 or 400 AD, we find that the dominant idea is the idea I'm presenting. that
Well,
that from the fields, where we make solitons, which they called monads, and from the monads we build structures, and the geometrical property of those structures determines all their properties. Did you know, in the days of the ancient Greeks, they had what are called academies, which would be our modern day university. And do you know what the sign above every academy was? Let no one ignorant of geometry enter here. Because geometry, they believed, determined everything in the universe. In other words, all the matter, all the properties of matter, everything was just if you knew the proper geometrical configuration. And they talked about monads, dyads, triads, all these different structures. And that's what, in my theory of elementary particles, I found is those structures and the vibrations of them and rotations of them that determine all the properties of the elementary particles that we have observed so far. And so that's a very interesting idea. But with the rise of naturalism after the Protestant Reformation in Europe, uh, what has happened is uh, there's been a big move to get away from religious ideas in science, and so they only want to accept the non-religious ideas, and so that's what you see is happening in our modern science today, and it's an issue that needs to be dealt with, and unfortunately the religious community has backed off from trying to do that. But in the past, they did participate in this, but now they're not. They're not very active at all. So it's a it's a situation where um, only a few people are aware of the issues, and they are not in a good position to do anything about it. I mean, you can publish books like I'm doing, but how many people are going to read those books?
Well, you
And
have the issue that the dominant political system now is atheistic,
yeah,
and they're following the communist socialist view, and they're dominating the discussion in the news media, and they're just dominating the all of the political discussion with their particular ideology, which is atheistic. And you can't even turn on a TV set and watch a. I mean, you know, when I turn on, you can't even watch a dramatic program on television without a lot of anti-religious themes coming out of the TV set at you. So it's obviously a serious problem.
yeah. So we've got two basic ideas, and during the Protestant Reformation, science made a lot of progress because it turns out that there were some religious constraints pointing in the wrong direction. Like the Catholic Church had some ideas that the Earth was the center of the universe, and they were teaching that. And when we realized that the sun was the center of our solar system, we realized that the Earth wasn't quite as important as we thought. And so anyway, we made a lot of progress due to the Protestants protesting. And but then other people came up with ideas because they didn't like the outcome of some of these discoveries. Like, for instance, in electrodynamics, they were attributing everything to the Spirit of God, which was in agreement with the Bible, which means that God was the source of all fields. Well, they didn't like that. So what they wanted to do was they wanted particles to be the source of all fields with charge. And so that's what was emphasized. But that's not the emphasis of Faraday, Ampere, Maxwell, and those people. They were religious and they didn't see it that way. But you can see their work has been reinterpreted and from a different perspective.
I see Cornelius has been drawing some pictures for us. So Cornelius, were you trying to explain something about magnetic fields?
No, I was just drawing what Harry was talking about and what Bill was talking about with the refrigerator magnets, basically, that they were, printed magnets that were basically the North and South Pole were printed in stripes. And the printing is on one surface, so then when you put the other two surfaces next to each other, the fields are so weak that there is no attraction to them. If you look up 3D printed magnets and stuff like that, they can print magnetic patterns, utilizing a technique, something like rare earth magnets are used, where there's a powdery compound that's magnetized and bound together. And you can actually, print your own 3D magnets and come up with magnetic fields that have all sorts of arrangements. But any way you look at it, there's still always a north and south pole that's canceling each other. Looking at like figure 7 that Bill had on his, for instance, it's really not a monopole. It's basically a magnet that's just in a different shape, just like two horseshoe magnets together. I've tried to put it up basically on my video, but because I don't have any way of getting online. But figure 7 there, if you look at the magnetic field lines that I've drawn, you can see that those are basically, the south is in the middle, but they go around each north pole and split. So the magnets are attracted to metal. The metal redirects the magnetic field out from the sides towards each pole respectively.
Well, show figure 8.
It's actually, figure Franklin. 8. Correct. It's not figure 7. There you go.
Here you see you've got two north poles.
Right, and that's what I've got: two south poles, two north poles. If you look at my image there, I don't know if you can see my image on. It should be a picture, and instead of my picture on the screen, it should be the image I've drawn. And I don't know if Franklin can enlarge that or not, or bring it to the center of the screen.
No, I think people can click on it if they want.
Okay.
On your video feed. But I think to Bob's point is that all of these things are being built out of geometric arrangements of regular dipole magnets.
That's correct, and that's why they're really still dipole magnets in which the north pole is either hidden or and it's like the ring magnets that have the south in the middle and the north on the outside edge. They show, I think, if you want to scroll up or down. Bill shows a ring magnet. I've looked over this paper because Bill was kind enough to send it. I think it's a toroidal type shape magnet field. The magnet in figure number 4, when it's stacked end to end and made into a ring, they, claiming that would be making a monopole magnet where only the south was on the outside. But you can't actually fit a ring together like that without actually forcing it and gluing it together to hold the north pole against the south, and then you will still have the north seeping out between the cracks, or through the you won't lose the north. The north will still be connected to the south if you were to able to So you'd have to actually force those magnets together to make a toroidal ring like he shows elsewhere on it. It's in his page elsewhere. I can't scroll up and down to show it to you, so there's another toroidal magnet there somewhere.
That's the way they make the unipole magnets. Yes.
Yeah, it's if you want to scroll a little bit, we should be able to. Yeah, right there, figure 5.
Figure 5. Yeah, shows.
So that you can't actually put those magnets together and create that without forcing them. You'd have to fight the magnetic pole that's inside the north, opposing the north, and the south, opposing the south, in order to get that ring actually put together to make a unipole magnet.
Yeah, what they do is these are what are called centered magnets. They're heated and they go together and become one continuous media, and so that's how they make those. But they have to have it in a restraining ring while they're heating it up, and then we take it out. And if you drop it on the floor, which I've done one, it just splits into many pieces because of the strength of those magnets repelling one another that's made of.
Right. So
Bill, I'd like to bring up another subject here on this issue here, which I'd like to hear your comment. If you go and you look at a book on electricity and magnetism from the 19th century up until the 1930s, they present magnetism from the point of view of the magnetic pole. And the magnetic pole basically disappeared in the 1930s, and they rewrote all the textbooks to make the magnetic pole disappear. And so, to me, all the if you look at the bar magnet in the picture here that we have on the screen, basically what Coulomb did when he came up with the magnetic inverse square law. Okay, so and they don't teach this in textbooks anymore. Coulomb said that the law of magnetism was the same as the law of electricity, that magnetic poles, conform to the inverse square law just like electric charges do. And he did experiments that supposedly demonstrated that by basically taking long, thin iron wires, and by making the wires long and thin, the poles became separated so that they looked like they were basically magnetic monopoles separated at the ends of this iron wire.
Yeah, I think that you can see a little bit of the history that way. But if there is no such thing as charge or current or mass, but those are properties of the soliton structures, then you realize that, and the soliton structure is similar to what we would call a toroidal current ring, because it has a magnetic field associated with it. It has both a north and a south side of the field. But you find that when you put these together to form a elementary particle, you can have an elementary particle that can be a magnetic monopole. Just the same way this thing was put together with real magnets, larger size. So the question is, can you do that? Is there a way to make a structure so that one of the two fields is not evident?
Well,
I certainly don't know the answer to that. I'm sure the physicists who deal in these sort of things will have great fun with that.
Well, see, that's what Winston Bostick and Arthur Compton were doing. They were trying to show that because of their religious convictions, they were trying to show that there were magnetic monopoles, and that everything was constructed of the fields, not charges.
Bill, do you have a reference to Bostic paper?
Yes, it's in this one. I'll be sending it out to everyone in the group as when this meeting's over.
Thank you.
I guess I just sent it out to Franklin. In fact, Franklin, you could just forward that to everybody if you want. And then they'd have that one's in color. The one that's in the newsletters in black and white, because that's all that we can print. And it's not nearly as good as the color one because you can see more stuff in the color. But so anyway, yeah, so the work of Winston Bostic and Arthur Compton, even though he received a Nobel Prize for it, is challenged today because we have what's called the postmodern philosophy of science, which makes each field of science a separate silo with different people that control each silo. And basically, they have removed the role of logic from the scientific method in most of these silos. So you can't, they don't allow people like Winston Bostic and Arthur Compton to disprove Maxwell's equations. They don't allow that. And so anyway, that's the situation we have. And if you look at the scientific method, you don't see any logic procedure that falsifies a scientific hypothesis. You don't see any hypothesis falsified because of an idea, an assumption. Like, for instance, take special relativity. It assumes the universe is homogeneous and isotropic. We know it's not. Just look at it. Just look at our solar system, look at our Milky Way galaxy, look at the overall universe. It's not homogeneous and isotropic. So that should be enough to falsify the theory of special and general relativity. But
No, I think it just basically means that the underlying field is homogeneous and isotropic. The field that everything begins from.
That's right.
So the underlying field is homogeneous and isotropic. It just becomes anisotropic when you create the waves in it.
That's right. So then it's not isotropic and homogeneous.
The underlying field is homogeneous and isotropic.
The underlying.
If everything was homogeneous and isotropic, we would have nothing would exist. But if the underlying field is homogeneous and isotropic, we would be fine.
Whenever you have any structure in the universe, it's no longer homogeneous and isotropic.
Well, getting back to the subject of magnetism. So, Bob, I think though initially you were asking a probing question about what is the nature of magnetism. Yes. So, you still have a probing question on, exactly. I mean, how can we speak of magnetism if we don't really know what it physically manifests as?
I greatly appreciate Bill's discussion here. It's very interesting. I would like to put forth the idea that there is no magnetic field, that there really is only one field, and what you do mathematically to represent that field is, for example, a Taylor expansion in parameters or other, and you come up with different terms, mathematical terms, describing that one field. And for some reason, for convenience in particular, we name individual terms. One would be a Coulomb field, one is perhaps a magnetic field, one is perhaps some other field, etc. But if you do algebraic manipulation, you can change what each of those terms are. So I'd suggest that really there's only one physical field, and the mathematical description is splitting it up, but that mathematical individual terms are not different fields. It's really just one field described several different ways or several aspects of that one field.
I don't think that's any different than what Bill is saying. Bill is saying basically you're starting with one field and one force, and the geometry of that force and the directions of the geometry of that force change the properties of that field and give you the characteristics of charge and the characteristics of magnetism depending on the motion and the geometry of that field.
which is why I was really interested in what Bill was saying this morning. Um, I've been doing a lot of reading on Weber's electrodynamics and, how what is the definition of an electric field? Well, it looks like you take all the force on a test charge, divide it by the test charge amount of charge. That's the field at that point, or that's the field at the location of that test charge. That's only one field. And mathematically, you split that up in many terms and name your terms if you want to. Um, so I'd like to throw out that there is no magnetic field. There's only an electric field, and it's an electrodynamic field. There's one field, and we just talk about different properties of that one field in different situations.
I think the confusion here is that the term of the use of word fields too. Fields basically, I believe, relates to the specific property characteristic. Like magnetic field doesn't mean that that's a physical, physicality that's separate. It means it's the characteristic. So you're just comparing that characteristic from area to area within the units of space. So you're saying how much magnetic field, how much of this field has a magnetic characteristic, how much of this field has a charge characteristic. So it's still all within the overall ether, or still within the overall initial founding force that it takes different geometries to create a characteristic or a property, and we basically define that particular property as a field. We also sometimes use saying, instead of saying property, we say dimensions, and that gets confused with the actual physical X, Y, Z dimensions, but it actually is like a property. You have a dimension of temperature, a dimension of density. So we when they start talking about fourth or fifth dimensions, we're actually talking about various properties.
Right. Thanks. Yeah.
I have a comment I'd like to make. I'm about to publish a book by William Hooper. It's called New Horizons in Electric, Magnetic, and Gravitational Field Theory. And what Hooper did when he was at the University of California at Berkeley, which is a pretty good school, is he measured the properties of electric and magnetic fields. Now, he didn't measure one electric and one magnetic field. He found there were three types of electric fields and three types of magnetic fields. And he measured 14 properties of each of those fields, and he showed that they were different. And so that is not, his work is not allowed for you to be able to see, but the fields he had that he was working with in terms of normal electromagnetic nomenclature was the electrostatic E field, then the time-dependent E field, which is equal to, in Maxwell's equations, minus dA over dt. It's the electric field induced by a changing magnetic vector potential, basically. And then he has the EM field, which is V cross B. So he has three types of electric fields. And so what he did is he measured the property. I'll give you the properties that he measured. He measured the spatially distributed energy of the field. He measured del cross E. They're all electric fields, but del cross E is equal to something different in each of these cases, and you can measure it experimentally. And he measured the integral around a current loop of E dot ds, and you get something different for each of these fields. He measured the behavior with respect to shielding. Can you shield this type of electric field? Well, you can shield 2 of the 3 types of electric fields, but not the third. And then they asked, do they obey Poisson's fundamental law with respect to the interior of conductors? And 1 obeys and 2 do not. And and it's, when you see this, you see that of the 14 characteristics, the different types of electric fields and the different types of magnetic fields don't have a whole lot in common with one another. And this information is not in any textbook. Even though it was published, the experiments were reproduced at many universities, it's not in the textbooks because it doesn't agree with the theories that we have, and so it would falsify all of electrodynamics, and so they don't want you to know about it.
Bill, I'm seeing a lot of William George Hooper books on Amazon. Is this another book that has not been published before?
No, but the books that are on there are if you were to, I've gotten them myself, and if you were to look at them, you will see that the original book was put out as a typed book and then just printed on paper and bound, with a plastic comb. And that book was then Xeroxed. And the Xerox copy is not very good. And that's what was printed. And so the reason why I'm going to put it out is so it's readable. And I fixed up all the diagrams that were deficient. And the text now is very readable, and it's I had to word process the entire book. But yeah, they're out there, but they're not easy to follow.
And when do you think you'll have that available?
Well, the copyright was 1974, and it's supposed to expire this year, although I hear that the government passed a law that extended those copyrights another certain number of years. And I've got to confirm that whether or not that applies to this book, because I could be sued for releasing it. The people that are putting the book out, they don't have the authority to put the book out, as far as I know. But Hooper and his family have all died. The people that worked with him in his laboratory have all passed away. So I don't know who would be the one to do that. I can't find anyone to ask for permission to publish the book. So I'm kind of caught in a awkward spot at the moment.
So I was looking at Amazon. So is it William George Hooper? There's I can only find 1 book in Amazon.
Yeah, it's William Hooper. Yeah.
Because he's got the book that's out here is on ether and gravitation.
Yes. And it's William J. Hooper.
William J. So it might not be George.
Yes, not George. So he was president and director of research for Electrodynamic Gravity Incorporated. He was professor of physics at Principia College after he finished his work at Berkeley. And the copyright is held by an organization called Electrodynamic Gravity Incorporated in Akron, Ohio. But none of the parties live there anymore. So, but yeah. So anyway, I hope to be able to publish that book. I've already word processed it. It's ready to go. I could publish it in 24 hours, but I'm concerned about a suit. So I'll probably get my son, who's a lawyer, to see if he can find out any more about it than I know how to do. But,
well, you could email it to people who are interested, I suppose. We're not going to snitch on you.
Well, you could. I could send you a PDF of the book. Besides the original book, I put some papers that he and another person at the Organization of Electrodynamic Gravity Incorporated uh, put together. A man and a woman basically sponsored his work while after he left Berkeley, and he did some more experiments and did some very interesting experiments that people thought were magic tricks. And so, but they weren't, but it looked like it to them, and because they were not anticipating that. He found many properties of fields that the regular experimentalists didn't discover.
Well,
And
it sounds kind of like what he was doing he was just really taking electrodynamics and trying to utilize that and say that electrodynamics was responsible for all force fields. And even the name you just mentioned, where the electrodynamics of gravity, seems like and like you said, also there's different types of forces and different types of fields, and one of them you said you couldn't block, and that would be equivalent to gravity, which can't be blocked.
well, but it's a field that we recognize in electrodynamics. V cross.
Now V cross B would not be gravity because there would be no cross in the gravity.
Uh,
Uh,
well, it depends on what produces gravity.
yeah,
See, the chemists, now this is another thing, and the chemists have discovered the force of gravity from electrodynamics because they work in factories where they are making various molecular compounds. And uh, what they have found is um, they often induce electrical vibrations in these compounds to when they're making them to get a higher yield so they can save money. And what they have found is that these compounds now weigh more than they did before. And they have discovered that. And then also the Russians have discovered the temperature dependence of mass. So you have an electric charge, and now its mass is changing with temperature. And so all these things are not currently officially acknowledged, even though many universities have now reproduced these results. And so when I derive the force of gravity, I'm just deriving the force between vibrating dipoles that are in atoms, and they're spherically distributed. So you've got vibrating dipoles going in all directions, and you average over that, and part of the force is cancels out due to the spherical symmetry. But there's a part that doesn't, and the V cross B is the part that doesn't, and that part is what causes gravity. So
Well,
my
I
work
think it's
agrees with that of Hooper.
yeah. I derive gravity before electrical and before magnetic. It is more in the sequence of there's mass first, and then there has to be mass first. Then there becomes from that charge, and from charge becomes uh, the magnetic. But you basically, they are all linked together, so you can work backwards and say, well, magnetic is responsible for electrical, electrical is responsible for gravitational. But it's a matter of they are all linked together. But initially, you can have gravity without charge and or magnetism.
the question is, how do you link the? I mean, Bob brings up, he's trying to say that there's only one field or something, and everything derives from it. But these things seem really different. So you have
Well, that's a key to mine.
You have charge, and if you stick like two oppositely charged plates and you stick a charge in between there, the charge clearly gets dragged to one plate.
Right.
Now it's like if you have two magnets like that and you put a charge between two magnets, the charge doesn't do anything.
Yeah, what Bob was saying too is that he's saying you start with a fundamental force, and all other forces are kind of derived from that, and that goes along with my view that there is only one force, and that force is the force of tension, and it's the geometry of the tension that creates the other characteristics of electrical, and then after the electrical is created, you can create the characteristic of magnetism. It's by various geometries of that tension distribution that you get those other higher level forces that you're talking about of electrical and magnetic, because electrical is polar and magnetic is polar, and you can't have magnetic without electric or without charge. But you can't have either without mass.
Yeah, so we have all these three different, like you got gravity, you've got charge, you've got magnetism. Now the question is, how can you have one thing, which is apparently blank empty space, because we know blank empty vacuum space can support all three of those. So whatever is supporting those fields is still got to be in the vacuum. And is it one thing then? You know, I think that it would be preferable that it be one thing, and that magnetic fields are not propagated by something which is different from the electric field, which is different from the magnetic field. That would be a big mess.
Right, so it's all propagated by tension in my theory. And I'm not exactly sure what Bill attributes his to. I know he eventually gets to monads, and I don't have monads in the theory. I just have the distribution of tension and the shape of the distribution of tension over time.
Well, I think, you know, Bill has mentioned this dichotomy between making the charge fundamental. That was one way of doing it, and versus you know, what William Hooper is doing, which is making the field fundamental. Now, of course, my argument always has been that every single field we know of is made out of some material thing, or logically, that's the way it seems to be, that fields have to be represented by something physical. So that is my main objection to that. So, you know, my preferred.
Wait a minute. The whole concept of field is that it's not physical.
No, I don't think so. I think that whenever you have a field, I mean, it appears non-physical in the case of electric charges and stuff like that. But if you have like a corn field, you know, that's a field made out of corn, that would be completely physical.
That's a different kind of field.
Right. In physics, a field is more of a mathematical presentation of the level of energy, the gradients in energy level of that particular type of force.
I would say that
I think physics has.
And well, that's where I completely disagree, in that we can't represent physics by just pure math. We're talking physics here, which means physical. It means there should be something ponderable that represents these things. So if I have a magnetic field in space, you think there's something different about that space than a space which doesn't have a magnetic field in it.
First of all, if you have a field like we're talking about, it's everywhere.
Of course it's everywhere. It doesn't matter. But I'm just saying that
and
there has to be something which is different.
In the ancient philosophers, they talked about this area between what we would call matter as the void, and the void has no mass, no matter. And the field can exist without there being a soliton in it, or it can have solitons. But so where we have matter is where we have solitons, and where we don't have matter is just the field.
Well, I think I would strongly disagree with that, because there has to be something physically representing that field. Now, it might not be ordinary matter, but there needs to be something of some kind of substance, because it can't be pure void, as Bill specifies, because I would think that a pure void would be incapable of representing, say, the presence of a magnetic field, because a void logically can't represent anything. So you can't have a strong magnetic field and a weak magnetic field in a void, because a void can't possibly represent either of those states.
Well, before we go any further, I mean, you haven't really defined what magnetic field is or electric field is. You really haven't.
Well, Harry, well, at our last conference, I did tell you what they are. So can you tell me what? Can you repeat back to me, just so? Because I kind of feel like
I can't make any sense at all out of what you said, so I'm not going to repeat it back.
Okay. Well,
repeat back something that didn't make any sense to me.
we'll try and make one more go of it if
No,
people
please
don't
don't.
mind.
Please don't. Please don't.
I mean,
And
do you want to have an explanation of the electric field and the magnetic field and the gravitational field, or
I
don't
think
you?
I think we've heard that before. I think we understand your interpretation of it, is what Harry's saying. I don't think
Well,
anybody I don't
well,
think
I don't.
anybody hasn't heard it and doesn't understand it.
Well, I just at this point would like to not talk about gravity because to me, that's, I mean, my point is I'd like to have a clear understanding of what you mean when you say electric field or magnetic field. And from what I've heard from the discussion, people have different ideas about what those words denote.
Harry,
And
I can't really specifically talk about the electric field and the magnetic field without understanding gravity first, because in my view, it originates from there. So I'm kind of out of the ballpark now.
that's not what I'm
Well,
saying.
I think that, we have agreement from mainstream about what these things are. The electric field is what comes out of charge. The magnetic field is what comes out of permanent magnets.
Yeah, but now you made an
The
assumption.
gravitational field.
You've defined the object based on that this is the source of electric field is charge. So now you made this your definition has brought into it the assumption that there's this thing called charge that creates electric field.
But the thing
We
is that
just
Harry,
talked about that, that's just not correct.
yeah,
No, I think
well,
that's perfectly correct. I mean,
I
if you
think what's
have an
missing.
object and
But see,
it,
Winston Bostwick proved that charge was not the only origin of electromagnetic fields. That charge was associated with fields, related to fields, but that fields were more fundamental than charge.
But that's
I mean,
exactly my point, Bill.
you can take that we have instruments, which will measure electric field. We have instruments which will measure magnetic fields. I think that's very clear what these two things are.
Well,
Well, tell us
I still
then.
think what's not clear is what a field is, because a field is just a representation of the relative intensity of charge from location to location. It's a gradient. It indicates the gradient
Yeah,
in the
but
intensity, and that's what the field is. It's not a physical thing.
Harry is
If you look it
asking
up
if
in
I,
physics, if you look it up under field, try to looking up under field in physics, and you'll get the proper definition for field, that it's not a physical thing. It's a measure of the physical field, just like an inch or a second. A field represents a what do you call it? Matrices of intensity levels over
well,
the area. That's what the field is.
it has
It's
to
not
be
a physical.
measurable. I mean, a thing that measures electric field is an electrometer.
It is the measure.
It,
Yeah,
That's what the
but
field is.
it has,
you
It's the
can't measure a charge. You measure the fields of the charge.
yes,
Right.
and you use an electrometer to do that. I mean, it's just like
Right.
a
So
voltage
charge
meter.
is something we made up with our imagination.
I think we could
The
really
thing
clear
we
this
always
up if
measure.
we just looked up field in the internet and you utilize field in physics, and that's all we really need to do. Look at the definition of a field in physics, because we are speaking physics here. We're not talking corn.
I mean, if you run, although that is a fundamental point I'm trying to make here, is that whole idea that the field is not represented by physical things, I disagree with that, just fundamentally. That I would argue that if there's a field there are physical particles representing that field. There must be.
Do you understand 5 dimensions?
No, I don't understand 5 dimensions.
See, and that's because you're not looking at dimensions as they're used in physics. You're looking at dimensions as they're used in geometry only.
And I think that is the proper thing to do. I think if you're looking at 5 dimensions, I think you are looking at something which is non-physical.
But a dimension has a different usage in the world of physics. The term dimension has a different usage.
And that term is, when you're going to the things which are like 5-dimensional, that I would say that that's a massively incorrect usage.
Because you have a spatial dimension is only one dimension, and it consists of 3 geometric dimension. And that's where confusion comes in, is because we utilize the term dimension in a couple of different ways, and we utilize it differently in physics than we do in geometry. And I think we need to look up dimension in physics.
Well, we're still talking about fields here. So
right. Well,
my
fields are also
claim
different.
claim is that a field is just any three-dimensional area in space where you can measure different properties. So, you know, it could be anything. Could be, I don't know, the color of light that's in there, or it could be the temperature, or it could be the magnetic field, which is measured by a squid device, or it could be a magnetic or electrostatic field, which is measured by an electrostatic meter. In any case, there's something in there that we're measuring using these instruments. So the question is what enables us to measure all these different things in the same space? So clearly we can measure electric and magnetic fields in the same space while gravity is going on at the same time. So the question, and we can do that inside of a vacuum. So the question is it logical to expect that all of those properties can exist without any physical matter of any kind? So
well,
that's the question.
We can measure sound in the same field that we measure radio waves, and they occupy the same space, but we wouldn't call it a sound. We could call it a sound field, and we can call it an electromagnetic or radio wave field. That we don't have any problem with the two of them existing in the same space, because one can go right over the top of the other. One is just a modulation of the other.
Now, that's not my point. My point is that the sound wave we know is mediated by particles. The question is,
which is mediated by charge.
We know it's mediated by fields,
gravitational fields,
between
right?
the particles.
Eventually, it all becomes fields. Eventually, we only sense things through the fields, through the force of the individual force. Eventually, we sense things only through in my view, through the interaction of tension in different geometries. But that's my view. Other people utilize a fluid type geometry and say it's a pressure situation.
Well, this gets down to some of the arguments we've been having in the email, which is that at some point there are no forces like electrostatic or magnetic, that really the only thing that happens at the very end is collisional forces. So if you have one particle, it hits another particle, and it goes off according to Newtonian dynamics.
Well, that's not the collision. That's not the fundamental. The fundamental is below that, what particles consist of. So it there again, it varies depending on the perspective of the theory.
Yes.
In the old TVs, the electron is moved by the field, not by collisions, to form the image on the screen.
Well, perhaps not. Perhaps it is collisions which are eventually pushing the electrons around.
We can tell it's not collisions.
How can we tell it's not collisions?
Because we see the collisions and we see the fields, and we can see that the fields are doing it, not the collisions.
Well, how do we know that the fields, which I claim are made out of something physical, aren't causing those tiny collisions? Because that's basically what I'm claiming, is that the magnetic field, the magnetic field is an electrostatic field, and the electrostatic field is due to a wave action, which is ultimately caused by just collisions. So that when you get down to the very, very just positron and electron, if there's nothing between them, then there can be no force between them. So if you had a separated positron and electron, they actually would not be attracted to each other.
Yeah,
in the TV that we have where we do electrons, we have action at a distance due to the tensile strength of the field. You don't have that tensile strength in collisions.
See, just exactly
So
what
you
Bill
have,
said. You cannot have waves without tension.
and you cannot have waves without particles is the other trick.
Well, that's the trick that needs to be
And but
understood.
but
Yeah.
but you
Tension
can have
between the particles
you can
due to
have
fields.
you can have tensile
Exactly.
strength. You can have tensile strength if you have a media that's connecting the two particles.
And that's a roadblock that you're dealing with. I think
That's
some of
not a
us
roadblock.
are beyond that, but not all of us.
I mean, that's not a road. We're just trying to explain things here.
I don't think Bill believes that you need the particles to have the tension between them. But I don't know if Bill can speak for himself, but in his case, in my case, there is just a tension field, and everything is derived from tension. So I don't need the particles. The particles are actually derived from patterns of tension, or emerge from patterns of tension. I see Lou is here. She's the one that taught me the word emerge. Thank you, Lou.
Well, let's go back and
From my view, it still seems like we're floundering around with a definition of what we're talking about.
no, I don't think so. I mean, charge and magnetism, I think is obvious. It's abundantly clear.
Well, you're denying it because you don't want to accept that you don't really have a clear idea of what it is that you're talking about.
I have
You
totally a
just
clear
have a
idea of what
fuzzy
I do.
notion that you just keep talking and then you talk in circles. I mean, let's not have a fuzzy notion. What is it that we're
It's not a
talking about?
definition.
What is it that you mean when you say electricity or magnetism? What do you mean when you say those things? Or electromagnetic wave? What do those things mean? What does that actually mean? What do those words mean?
Electromagnetic wave is a compression wave through a medium. That's what I mean by electromagnetic wave.
That's what you mean.
Is
It
that clear?
doesn't mean anything to me.
Well, I'm
Means
just explaining
nothing
to
to
you what
me.
then what does it mean to you?
Now I'm asking you.
And I told you what it means to me.
It doesn't mean anything to me. That's the problem. Do you understand what I'm saying here?
So you
It's
don't
the same
understand that
issue with field.
electromagnetic.
Field. Everybody here has a different idea of what field means.
So you don't understand that what I mean by electromagnetic wave is exactly the same thing that people mean when they say sound wave. Sound wave is a compression wave through a medium. Electromagnetic wave is exactly the same thing. It's a compression wave through the medium.
And there's quite a
Okay,
discussion
so
going
how,
on about that too, because in the emails, there's a lot going on about whether it's a transverse or not. An electromagnetic wave being a transverse wave gives it polarization, which your sound wave does not have.
Sound wave.
There was quite a conversation going on about that too that wouldn't probably need to be expanded upon at this moment.
well, that's a good point, Cornelius. That's why it can't be a longitudinal wave.
That's my understanding, of course.
Well,
everything.
Cornelius, you've been watching the arguments go by. I mean, Robert and me, we believe that that the photon, which has to be created within the vestibule of the atom, is quantized, and as such, it goes off in a light ray, which means it's kind of like a bullet. Now, it's not a particle, but it's particle-like in that it has a limited finite extent. It has a limited, diameter that it goes through space as, and the polarization filters are very easy to explain. I mean, if the only argument you have that light is a transverse wave is because it obeys polarization, then all I have to do is provide an alternate explanation for how that works, and that completely disproves, or at least eliminates the ability for you to say that that's a proof, because that's very, very, because you're not detecting any of the transverse component in your so-called explanation for why it's transverse. And this is my argument. So all I have to do is show some plausible explanation for polarization that does not require light to be a transverse wave, and then that completely disproves
You
that.
said some plausible explanation. I don't think that's a scientific criteria.
I think it would have to be a
Monopoles
proven
science.
explanation, I would think, in order to be a valid theory.
Well, you would
It
have
would
to
have to
also
be,
prove, you'd have to prove that light is transverse and it goes through like the rope through the picket fence example.
Well,
I don't
you'd
think
have to.
that have
There,
done either.
it's not a rope because it's not a single dimensional like a rope is, and you're already aware of that.
Yes, I
You
mean that's why.
but you consistently use the rope as an example that it could be like a rope, but you know it's not a rope, so why use that argument? You know,
Well, exactly.
I have
That's.
stayed out of that argument basically on the emails because I know it's pretty well fruitless to speak to it.
I mean that is my first point. That light is not a rope. So how can you possibly say anything about light by using a rope?
Well, right now we're speaking over the internet, which is probably somewhere transmitted over fiber optic cables, which fiber optic people take very, very meticulous care to make sure that the polarization of light going through the fiber optics is correct in order to get a good distance without a loss of signal. And, you know, so there's preponderance of evidence that the people that are actually using light pay a lot of attention to polarization. You can take pictures of
Yes,
things
but that
with
does not prove the transverse nature of light.
no, but you're talking about just going and taking light and running it through two polarizing filters. You can also take a polarizing filter and put it in front of a light and shine it on something and get that polarized light shining back at you. And if you turn the filters, you can actually block out the filters. You can polarize light and you can shine it on a plastic material and you can put stress in the material, and the polarization can detect where the stress is based on the difference in intensity of light coming back from that stressed material.
Yes,
A lot of those things cannot be explained by a longitudinal wave.
Well, the thing is that yes, it can be. If your longitudinal wave is traveling, if the longitudinal wave is traveling in a single soliton pulse, and it travels like a particle, then polarization is easily explained by if you take all the light waves which are coming in every which direction and you put it through a polarizing filter, which is very much like the picket fence, except it's much longer. So it's like you spray a whole bunch of bullets in every which direction. And now eventually the only particles that are going to be able to get through like the vertical polarizing filters are the ones which are traveling up or down, the ones that can fit through the slot.
I've kept up with the emails. I don't need to hear it. I mean, maybe others do, but
well, yes, I'm explaining it to Harry. So that the bullets are going either straight up or down through that slot.
I have no idea what you're talking about. Bullets. I mean, bullets don't mean anything to me. I mean, I don't think of light as a bullet.
Well, I think that's what you need to do. That's the point. You got to think of
no,
light.
I don't think so, because bullets don't move.
Remember that I'm a radio engineer, and you know, I think in terms of I don't think of bullets. You're talking about light. No. I think about radio waves. The wavelengths are
radio waves.
The phenomenon is different. So
yes, they are.
So you're trying to argue to me, you know, based on a particular model that you have. You have a particular model, and you're trying to tell me that model is universal, and I don't see it.
No, it's not. I mean, a major. Can I please get this point across? This was another point, the major point in the emails, which was that there's a difference between radio waves. I mean, I think Roger wants to think that they're all like bullets, but I don't think so. Radio waves coming out of antennas are continuous. You know, they're a continuous wave.
No, they're not.
But light which is coming out of atomic processes, specifically electron transitions, like visible light, they are being generated in a quantum fashion. So if you were to imagine this wave in a wave pool, it'd be like a single bump. You go like, boop, and then the wave would be a single bump, that's called a soliton, that would just travel across the wave tank as a single bump, right? It's not a continuous thing.
Like a tsunami.
One bump. Yeah, like a tsunami. That is what a visible light wave is like.
Like a fish traveling under the surface of the water, making a little bump as he goes.
Now, the claim is that if that travels like a bullet and that it doesn't spread out. I mean, this is one thing about the visible light is that it doesn't disperse. It stays in a specific packet. I mean, you could locate the photon in like a certain volume of space as being a compression wave that is traveling very compactly, but
No, you
it'd
can't.
still be a compression wave.
Compression waves diverge. Only
No, I'm
tension
saying,
waves.
no,
Only
I'm saying,
tension waves converge.
no, because of the quantum nature of how the light is generated and the quantum nature of the medium, it doesn't disperse. That would have to be that would have to be a postulate.
All pressure waves disperse. Only tension waves converge and stay packetized.
Well, this would have to be a postulate that it doesn't.
Well, experiment with it.
I mean, this is what light appears to do, that you create a bump of it, it goes off like, I would like to say bullet-like, but it's like particle-like.
You would like to say bullet-like, but if it travels bullet-like and not wave-like, then it's going to travel at the speed of the originating source.
No, but it is a compression. It is a compression wave. It travels according to the speed it's allowed to travel in the medium.
So
it is a wave.
It's just a packet, a single wave, if you want.
It's just a single wave.
You say radio waves are contiguous, but I can create a radio wave pulse that goes up and down an antenna once, and I have a pulse. I have exactly the same thing, just much longer wavelength.
Yes, you can do that.
And I can also take an antenna and plant it vertically, and I can take another antenna and plant it horizontally, and the horizontal antenna won't pick up hardly a darn thing, but if I plant it vertically in parallel with the transmitting antenna, then I'll finally get a signal because they're in the same plane of radiation because they are transverse.
No, I mean, there was an article that was sent around about that basically, I mean, we're talking about pressure waves, and there have been experiments where, you know, you do orient the antenna elements so to either theoretically catch the transverse component or theoretically catch the horizontal component. I mean, that can be done. Now, I don't have the exact reference for that, but the conclusion is that they could really only detect the longitudinal component, not the transverse component. Apparently, the transverse component cannot really be detected.
That's because we have the plane of the Earth we're dealing with also. If you do this out in space, it's differently. You're not interfering with the ground plane of the Earth. Harry knows all this because he's a radio man, like he says.
Yeah, well, he's a radio man, but that's not and
you're a bit banger, which is a computer programmer. So I think there's you have done an extensive amount of studying and research on the internet, but I think Harry's a little more familiar with radio waves.
Well, my question is this. I mean, what Franklin is saying, it seems to me that you cannot have a material medium that transmits transverse waves. There's no way you can have a medium, a physical medium. He wants to have a physical medium. And since physical mediums can't transmit transverse waves, therefore the wave has to be longitudinal. And so he was going to deny that electricity and magnetic waves are transverse because he can't make them go through his medium. That's my
I think a lot of seismologists are going to have a real problem with that because the people finding oil to run your car are using the difference between transverse wave propagation through the Earth and longitudinal wave propagation through the Earth and determining that where the transverse waves are no longer reflected because they encounter a pool of oil, and they call them shear waves as well. But you can say that, transverse waves certainly can go to the Earth, and I think you would really be upsetting a lot of people saying, well, how in the world did I find that pool of oil for you?
That is not relevant.
I think the issue is
Harry is correct.
Franklin's
You're correct.
ether medium does not support transverse waves. I think
does not support transverse waves. You are absolutely right.
And that's why Franklin has to argue so explicitly against transverse waves because he doesn't have a medium that is a solid. And his solid.
That is absolutely correct.
But the reality is no wave can be created without tension, period, regardless of whether it's in a solid or not.
And no wave can be created without a particulate medium.
Well, gentlemen, now you've limited yourself with your assumptions, so that's.
What do you need, Jim?
This is Bill. Um, I want to let you know that you can buy a electromagnetic longitudinal wave detector on the internet. It's called Experimental Life Energy Meter, and you can see that the regular light that we have is not longitudinal, but that the energy coming out of living cells is longitudinal and can be detected by the longitudinal detector. And so you can easily show with that detector that regular light is transverse because it can't be detected as a longitudinal. Longitudinal detector can only detect longitudinal waves inside a capacitor. So you've got to bring whatever your detector is getting inside of a capacitor where it can be detected. And and it works very well. I have one at my house. It detects life energy, but it won't detect a light bulb when it goes off.
Well, I guess my objection boils down to I don't think that we should define the phenomenon in terms of the theory that we want to use to explain it. That's what I
Well,
object to, what Franklin says.
that's what we all have to do, right? This is science. We come up with a hypothesis of
No,
what we
you want
think
to
where
explain the
the way
phenomenon
world.
based on the theory that you have. So you
Of
define the
course,
phenomenon in terms of your theory, and I don't, I have a problem with that. I don't agree with that particular
that's
approach.
that's what we all do. How else would you do it? Do I have to define it
Well,
in terms of your theory? As
but what
what?
you do, so now we've demonstrated to you that light is not a longitudinal wave, and we've explained it to you. And because your theory basically can't transmit transverse waves, you say that they don't exist. You just deny the transverse wave. So to me, that's just illogical.
Well, what's also illogical is that there's no experimental evidence of the transverse component. I've been keeping asking people, if you think light is
We just
transverse,
explained to you what it was. I mean, Cornelius
there
just
must
explained it to
be
you in
be.
detail.
Then what's the experimental evidence? Where's the transverse component?
The empirical laws of electrodynamics, Ampere's law, Faraday's law, Coulomb's law,
That's
those
not
are the
experiment.
evidence for transverse waves.
That's not experimental.
That they
It's
are
all
experimental laws.
not
They cover all
experimental.
the experiments we've been able to do so far.
Then where's the experiment that shows the transverse component?
Well, a transverse component is also needed because you have to be able to explain the right-hand rule and why a magnetic field is perpendicular to the electric field, and the electric field
And
is
what does that have to do
perpendicular
with?
to the direction of motion.
And what
Because
does
the
that have to
origin,
do with the
because
transverse?
because the origin of the wave is an electromagnetic wave and it comes from the motion of the electron. So you have to understand that the electron itself has got transverse waves within it, much like Bill's demonstration of the toroidal ring electron. Bill's toroidal ring electron is somewhat close to what I believe is a correct motion of charge. The only difference is that I see Bill's toroidal ring as being an electron in linear motion,
Still,
taking on the shape of a
there's
toroidal ring.
still zero experimental evidence to like support this picture of this varying electric and magnetic field.
But it's a logical sequence because you cannot explain those characteristics of the electromagnetic interaction of being right angles, the right hand rule. You cannot explain them with longitudinal waves.
Yes, you can. I mean, but the magnetic field is something completely different than the electrostatic field or the EM waves.
But
The EM waves.
we just said all those forces are derived from a single force, and you have to decide, whether that's what you're talking about. And they are just different geometries of a single force, and it just happens to be the geometries are transverse included.
Still, no experimental evidence that there's this varying magnetic and electric field. And as was pointed out before, is that they're always shown to be in phase, which is probably impossible because the magnetic always has to lag the electric, or the electric always has to lag the magnetic. So that picture can't possibly be true.
Well, look up fiber optics and see how much attention those fiber optics people pay to the fact that it's not polarized. And look up the radio waves and see how much attention the radio people pay attention to the orientation of their antenna so they can get the strongest signal.
Once again, polarization does not prove transverseness.
You just don't want it to exist because you can't make your theory work.
No, I don't think it exists because there's no physical evidence that it actually happens.
We just explained to you that there is. I mean, you know,
no one has given me a single experimental and a single experiment showing that the transverse component can be physically measured. Nobody has given me any experiment to directly measure that.
Well, I mean, you know, the polarization experiments have, you know, I did that when I was 10 years old. I did polarization experiments when I was 10
And I'm telling you that how does polarization exactly show you what a radio wave or anything is doing?
Well,
all that's showing you is that it
don't want it to.
The thing is that a light wave is so small. I mean, we don't know exactly what that is. We do know it obeys these polarization things, and it could obey those polarization things because you're just blocking a particular vector direction of a light ray. So if you block all the vector directions so that they're only going up and down, and you put another filter across that blocks only the light rays are going horizontal, then when you put those two filters together, of course, they will completely block the light. And it doesn't, and the object does not have to have any transverse component to do that.
Well, I suggest you read some books on this subject. I mean, that's all I can tell. All I can say.
Well, I would suggest that you go find some evidence that light actually has transverse component.
It's in the textbooks, Franklin. Read them.
And they all are just based on polarization, which is a really indirect way of saying that it's got the transverse component. It's highly indirect.
Well, I mean, you know, this is kind of like, you know, reality isn't real. You know, we're not talking physics. We're talking fantasy world. You know, I don't know. I mean, I can understand this conversation sort of makes me think, and that I understand now why mainstream basically does physics and teaches things the way they teach it, because, you know, that way they can control the conversation, they can control everything, and they don't allow any discussion of the science or the fundamentals, because if they do, they wind up with a conversation like we're having, which is just chaos. You know,
well, if mainstream does its job, what they're supposed to do is teach us to study for ourselves and research for ourselves.
I agree with that. Cornelius. I do. But you know, but if you don't have some kind of background and framework, what you wind up with is a chaotic discussion, just a lot of different opinions and nobody being able to communicate with anybody else, unless you have some concepts that are fairly well defined that we can use to communicate. And Franklin's saying, well, I deny the concept of polarization and transverse wave, which renders the ability to have a conversation about electromagnetism null, in my opinion.
Well, the fact is, how much do we know about electromagnetism? I mean, from mainstream, they don't know what charge is. We don't physically know what the magnetic field is. We don't know physically what gravity is. So isn't that lack of knowledge just basically invalidate any conversation about electromagnetism?
I don't know. Currently, I'm designing a current transformer, which involves electromagnetics to a very, very strong extent. Previously, I've designed electric motor rotors and electric motor field designs. And that's just the past few years of my electronics career. And I've worked in optics, and I've worked in, you know, since 1973 in electronics and magnetics, and Harry's worked in radio, and I think we have a little bit of an understanding of it. I've also taught classes on it, so I might not understand it, but I think I know a little bit about it more intuitively than just what the fundamental textbooks taught us as a beginning and a foundational piece of information.
Yes, but if we don't know what charge is, then how can we really say anything?
We have
Well,
to hypothesize what charge is, and we see if they react, if things react the way we expect them to, based on the hypothesis.
You had a comment, Harry?
well, I don't know. Yeah, that's, you've kind of thrown out a statement that is a bit more tricky to deal with. You know, I can only say to you, I would suggest that you read some books on electricity and magnetism and you study the history of electricity and magnetism, and I can provide you with ample sources of information and the history of electricity and magnetism. I've written a lot of papers on this, and I suggest that you read those and try to figure it out on your own.
Well, that's what I have. And I mean, the history shows that we haven't figured out very fundamental things like, what charge is. And,
Charge is, as I think Bill explained this earlier fairly clearly, and that charge is a created entity that's useful in building up a framework for understanding. I don't remember. Bill said it much better than I could say it. What was it that you said, Bill?
Well, let's take Coulomb's law, the force between charges. What you do is you measure the field of each of the charges of each of the what so-called charges to get an idea of the strength of the charge, and then on that basis you can write down a force between the two bodies that have a charge, and so that's what we have done. In order to get an equation, force equals something, we had to define some kind of constant, because we couldn't see it in the sense that you can see some things in nature, like billiard balls you can see, but you can't see the charges and things of that sort.
I mean,
And so,
is this like the empirical? I mean, there's things we can empirically measure by scientific experiment, and we can write equations to them, and that's fine. But that still doesn't mean that charge itself is imaginary, or
yes, it does, because if you asked Coulomb, he would have told you that. Coulomb wrote down Coulomb's law. He says we don't really know what charge is. It's a constant that we put in our equations. It seems to be quantized, but that's all we know.
So, but I think we can know more.
We can't do precise work in science if we don't use equations with an equal sign. If we just say the force between two bodies is proportional to something, that's not as good as saying it's equal to charge 1 times charge 2 over r squared.
Yeah, but that is that.
Hold on
charge
here.
is something.
I want to inject a comment here. In electrodynamic and classical electricity, charge, you say this thing Q is equal to the surface integral over the surrounding surface. So that says to me that charge is really nothing more than a measure of quantity of field.
That's right. Everything is measured in terms
summary,
of field.
Harry.
So charge is really basically a quantity measure of field. That's all it is, really. And then now you're going to say, what is field? Okay, now we got it, and so that's the issue there.
Yeah, and you can't say, if you don't know what charge is, that charge is the creator of the field.
Yeah, I think Bill goes a little farther than that. Bill also explains how the charge becomes an electron, how charge makes a pattern to become an electron, and how the amount of charge on an electron can be explained by the wave pattern around that.
Well, whatever charge is, it has to be something that's measurable around
we just
an electron.
To you that charge is basically a measure of the field, the amount of field that's there.
No, I
is
think
a measure of the quantity of field.
That would be a measure of the electrostatic field. But
Correct.
that comes out of something called an electron. If you have an electron, you can measure that field.
No,
and
that's not what it
increasing
is. It's a measure of the quantity of the field. Now, the mistake is when somebody says, oh, there's this thing called charge that exists inside the particle, okay, that creates the field. That's where you get into the circularity of the discussion.
I think that it would be more proper to say that you have, I mean, what you said was actually true, which is that there is a particle, and around it, it generates the field which we measure.
And what I've always said is the particle is the field. As the intensity of the field gets stronger towards the focal point, we recognize its characteristics more, but the particle and the field are inseparable. The particle is the field pattern. The particle is the field pattern.
That's a good way of viewing it.
Because the only thing we really sense is the interaction of the field patterns with other field patterns, and that's where we recognize the entirety of existence is through the interaction of fields, regardless of how large or small those interactions are.
Right.
Well, I would disagree with that, because I think the reality is that, you know, we interact with, you know, material substances, you know, like,
which is composed
like
of billions and millions of, which is composed of billions and billions and trillions of interlocking field patterns.
I would say that's because it's due to interlocking matter particles.
We can see that. You're just interacting with a bulk modulus of field patterns.
But fields, see, I have a hard time seeing fields. Like I have a hard time seeing the field for which the light is traveling through. So it doesn't have the same kind of reality as a hard, like, cell phone.
You can see the fields with a compass, with iron filings.
Yes, but the field has no solidity.
You
like,
can't
not
see
like
the electron
phone.
that way.
No, I say you can't see the electrons. You're seeing the electrons bouncing off my phone. So you're
seeing
the
interaction of light with this phone, so therefore you're seeing it's interacting with the field. The only reason you're seeing it is because your phone is interacting with the light. And the only reason you're feeling it is because your phone, the atoms and fields within the phone, which is a group modulus of a whole bunch of fields that are attracted to each other or that combined with each other, are interacting with the atoms that are a whole bunch of fields within your body. And the size of those fields are so minuscule that you just look at the group modulus and say that group modulus is an object, but in actuality it's a group modulus of field patterns.
All right, well, it looks like we've come back full circle. We always seem to be getting back to this whole question about what's fundamental fields or particles, but we are at the top of the hour here. And so this has been an interesting discussion. I thank everyone for participating. And so to summarize a little bit, I think we were talking a little bit about the magnetic monopoles, and it looks like there was a paper by Bill Lucas. I guess if you really want the paper, I have it. You can send me an email, or you can send an email to Bill, and we can forward you a copy. It's apparently they don't have the most recent versions of the Common Sense newsletter on their website. They only have older versions. But it seemed that that these monopoles are manufactured out of regular magnets, and so it's not quite the same thing as an individual like charge fundamental particle that somehow is a monopole. And then we started getting into some discussions. Let's see, what else did we talk about here? About just basically the nature of magnetic fields and how they work. And finally, of course, it always comes down to what is fundamental here, and how do we explain the presence of all these fields? I mean, we were discussing what is a field and how are they different? You know, we have the charge field, we have magnetic field, we have gravitational field, all seemingly existing in the same space. And so are those all the same aspects of the same thing? I think a lot of us would agree that they are all aspects of the same thing. And we did get into a discussion about the whole nature of light. There's been a lot of discussions about whether light is a transverse wave. Now my argument has always been apparently the only evidence we have for light as a transverse wave is the observation of the effect of polarization. And that apparently is the entire breadth of the evidence for transverse waves for light. And so my argument being that, well, if it was transverse, then you should be able to measure the vertical displacement in an experiment, and no one's been able to do that. And so polarization on its own might be good evidence that it might be transverse, but it's definitely not the final word. And Harry is right, is that, I argue against transverse waves because my medium is a gas, and that gas simply wouldn't support any kind of transverse wave like that. And it just doesn't make any sense for a light wave to travel as a transverse wave because it wouldn't be localized. It's transverse waves, like in an earthquake, travel like the entire distance and volume of the Earth, whereas light appears to be like these little bullet-like things. I mean, when they react positrons, electrons, they generate gamma ray, which is an EM wave, and it hits a specific spot on their detector. I mean, it doesn't spread out. It is very much like a little bullet that hits the detector walls, and they can tell, they're exactly 180 degrees apart. They can measure the exact energy that those things have. It doesn't generate this widely spread wave that spreads across all of the detectors. It's like a bullet. So it doesn't sound at all like transverse phenomenon in that case. But like I said, we are at the end of the hour. So thank you for participating, and hope you will come to next week's talk, where we will continue talking about things that mainstream won't touch. All right, so with that, we'll do it for now.